Welcome in this tutorial about using Sofa for SoftRobotics. The aim of this first tutorial is to give you an overview of the Sofa graphical user interface and also to introduce you how to write a very simple Sofa simulation. So let's start. I will run Sofa from a terminal with the -E option. The -E option activates the live coding capability of Sofa. This means that while you are changing the simulation description, the changes are automatically propagated into the graphical user interface. Let's start. By default, Sofa is loading such kind of scene. We will not use it. We will immediately load one that is part of the SoftRobot plugin, which is called SoftRobot.py scene. When it's done, a new window should have appeared. This window is called the doc browser. You can show it and hide it using the Help menu. The doc browser is showing the documentation associated with our plugin. It contains a set of tutorials that you can follow and a set of thematical documentation. Let's start to do the tutorial. In order to do this tutorial, you need to have a working version of Sofa as well as a plugin that is called STlib. This STlib is not mandatory to make a scene with Sofa, but it's a kind of a template library for Sofa, which means it contains a lot of prefabricated objects that should ease the writing of Sofa scene. So it's much easier for you to start with Sofa with using the STlib. In order to make this tutorial, you also need to have a basic knowledge of the Python programming languages. Actually, you can write scene with Sofa in other languages like XML or JSON-like languages called PSL, but all this tutorial will be done using Python. If you have never used Python, you are advised to follow this tutorial. Let's go now for the first step of the tutorial, where you will be in charge of setting up a simple scene. You can actually try a scene by clicking on this button, and it should load a simulation scene into Sofa. I will now take some time to explain you the graphical user interface. A scene has been loaded. It's composed of a floor and a cube. There is a 3D view that allows you to see the geometrical properties of the object. If you click on the animate button, it will start the simulation like that. There is also a second very important view, and this view is called the SceneGraph, because in Sofa all the simulation are in fact represented with a SceneGraph. And this SceneGraph contains two kind of different entities. One is node, which are the gray one here, the gray circle, and the other is component, which have a square representation. If you now go to the floor node, you can open it and you can see it's also composed of several components and child nodes for collision detection and for visualization, so rendering. Let's now speak a bit about the component. So this floor object has two components. Each component has a type, which is the mechanical object, and a name, which is here mState. When you double-click on any component into the hierarchy, it opens up a new window, and this windows will show you the different data or properties that are owned by this component. In this case, this component is specifying the mass of the object, and here you can have multiple ways to actually specify the mass of the object. Into this window, you have also some extra panels that allow you to show debugging information. as well as information about the object, from where plugin it is, and you can also have a message panel which show the warning, error, and information messages that this component is generating. In this case, you can see that inertia, the mass matrix I provided is probably wrong and need to be fixed. Okay, there is also another view. For example, here you can actually display. So here, everything that is displayed is made explicitly from the SceneGraph by object called OGL model visuals here. And for the cubes, we can go to the visual object here. So if we unchecked it, it will disappear, but the object is still there, and we can activate it that way. It's possible to display other information when we are debugging scenes. For example, you can show the behavior component, which means what kind of forces are calculated internally to prevent the cubes to go through the plane. You can also display collision geometries, and actually we can even hide the visual one and have and display only the collision geometries. And so this is a kind of very useful view for debugging purpose. I suggest though now that you start yourself making a scene, and for that you just have to click on the write it yourself link. This will load an empty scene, and you can get the associated source code by opening the file in an editor, which will use the default editor on your system. The scene is a very empty one. It's made with Python, and it's a full Python, so you can just write any code. And there is a create scene function that must be there, because this is this function that Sofa will call to each time the scene is loaded. So when you save the file, this function is executed. I saved it, and you can see in the console that the lines have been executed. This is useful to now create and add element into the scene graph. So the first thing you can do is actually add a child node to the root node, and not create object but create child, and you need to specify child with a name. And if you want now to add some component to this child node, you first need to get a reference to it. So it's a C, and we can create an object. I don't know if you remember in the previous scene I showed you that to do the visualization we were using something called an OGL model. So this is the component we will add now, and it's successfully added. And of course nothing happened because we don't have specified yet where the geometry comes from. So I will specify the name of the file name where the geometry will read from. Okay, so it's a very basic geometry. Of course you can cut and paste this pattern. So that you can have multiple gears into your scene, and we will change their location so that they are not at the same place, and probably do something like that. Okay, maybe it's not really clear on this view where are the axes, the reference frame, and a good so it may be a good idea to add them with the create object. So it's possible to visualize the axis by adding an OGL frame into your scene. It's not OGL frame, sorry. I forgot the name. Oh, it's a scene frame. So let's go back to our scene, OGL scene frame. Okay, so now we have this small reference frame on top of the 3D view, and a very basic way to remember which direction corresponds to which axis is to remember the color coding, that most of the time it's RGB, which means red is the first component, green is the second one, and blue is the last one. So if I want to move my third object along the green axis, it corresponds to the second component here. So let's put that on top of the first one, that way. This is the end of the first step of this tutorial. If you are doing it alone, it's possible to show the code directly into the doc browser, and actually there is a hyperlink to the different components we are using, so you can just click on them and go to read the documentation. At the end of this step, you should be able to load a scene with Sofa, understand what is the -E option. You should be able to add a visual object, which are here our 3 OGL model in a scene, and you should be able to move them into the 3D space. And you are also able to visualize in the graphical user interface the different properties of any Sofa component by just clicking on them. Now, in the second step of the tutorial, what we will do is to actually make a reusable element out of the gear one we made. In general, it's a very good practice to avoid cut and paste. So the idea is that instead of repeating all the time the same pattern, it's much better to take the generative code, put that in a new function, and this function will be in charge of generating the gear. So this is what I am doing right now. I saved it, but there is one Python error that say one argument is missing, and of course because I need to say where I want to add the gears. And now it's done. We don't see it because probably we are not at the right location, so I moved the camera farther from the center of the scene. So currently, if we use multiple gears, they will have exactly the same names and same location, so we need to add parameters to the function to let the user of the function to specify the name. So now we can have gear 1, gear 2, gear 3. Like that. And it's also a good idea to do the same for the translation. So we specify a default translation. We pass this translation to the create object function, but we also expose it to the one calling the library, to the one calling the function, like that, and probably here. And if we want to be really neat, we can add some coloring scheme like that. Which allow us to specify the color of the object. This is the end of the second step of our tutorial. In the last step of the tutorial, we will transform this gear into a mechanically simulated object. If you remember correctly, in the first, when I showed you this scene, the floor object or the cubes have a lot of different elements, and all those elements are needed to make an object that can be mechanically simulated. All those are needed for collision. These two are the one you know. Actually, you know the OGL model, which is for the rendering, and this one are for the collision detection. And we don't expect you to type in your scene each time all those components, and that's why we have made the Sofa template library that contains pre-made, prefabricated templates. So if we want to get the rigid behavior, we are searching into the documentation, and we can see that there is a package that is called STLib physics rigid, and that is into these packages there is a rigid object, and this rigid object has a set of arguments, and actually you can see here the structure of the object that is implemented into this template. So we will use this template to enrich our gear description, and we will do that first by importing the STLib physics rigid. So from STLib physics rigid, import rigid object. Of course, nothing happens because here we need to replace the OGL model only with the rigid object templates, and we will specify the right translation and color. Oops, something goes wrong because something goes wrong, and you can see that here with this small sign. This means that there is a messages that popped up here. Actually, we forgot to specify which mesh we are using, and it's very visible here. There is one attribute that is called surface mesh file name to specify the mesh, so I will add it here. No more error. But here you can see that the rigid object have not been added to the gear 1 node. And actually we don't need these nodes, and we will immediately pass by the name to the rigid object templates. And so now we have different gears, and all of them contains a fully working mechanical object. Actually, we can now just animate everything and have all the elements falling. Okay, so let's remove some of them, and what we will do now is to add a floor to this scene to avoid the gears to indefinitely fall. So let's add the floor object. So let's first import it with this line, and then let's add it to the scene. Something goes wrong. The name floor doesn't exist, of course. Now it's correctly working. And the floor is very close to the gears, so we will not see it falling. So we will move the gears upward, which means moving it along the green axis, which means the second entries. Okay. Good. If we simulate the scene, the two objects are free falling. This is because the floor have not been specified as a static object. So now only the gears is falling, and it's passing through the plane because collision detection is not yet activated. And this can be done with some template from the STLib scene. Import contact header. So something goes wrong, and the error is because we have forgotten parameters to the contact header templates. So let's go to the library to see what's wrong. And yeah, here it is. We can see that the contact header has two parameters that need to be specified. One is the alarm distance and one is the contact distance. The alarm distance is the distance at which collision detection will start be taken into account, and the contact distance is the distance that will generate a collision response, at which some forces will be generated to prevent intersection of objects. So I specified two values for that, and now I should be able to see the object falling, and it doesn't pass through the plane anymore. If you remember correctly, you can activate the rendering of the different contact forces and mechanical elements from this view. Here we can see the red line, the red dot that show the contact points. Okay, we are close to the end of this tutorial. I just want to show you some other features that may be useful. For example, when you are animating an object, it's possible to open the mechanical object properties, for example, the one that contains the location of the object, and we can actually see that the value are changing, which means the object is moving. It's also possible to change the value manually if you need to edit or tune or change something. So this is the end of this tutorial. I think that just a small summary. So during this tutorial we have shown you the graphical user interface of Sofa. We have spoken about the SceneGraph, the nodes, the component, the Python API, and we have introduced rigid object, and so now you should be able to make a scene that contains several rigid objects, graphical objects, and have them all interact all together. You are strongly advised to follow this introductory tutorial with one of the other tutorials. I will just remind you where you can find them. Again, into the Sofa SoftRobot plugin main browser,